Well, welcome back, everyone. And it's official. We can get started. It looks like you might be our representative on Zoom today, Rochelle. Thanks for making it in. And for our goal today, we're going to finish off example 6, finishing the next example, and that's chapter 17, moving into chapter 18. But before we get into any of that stuff, we should definitely scroll down and discuss upcoming exam 2. Like we mentioned before, I'm going for about 5 problems. I have one problem in chapter 11, pretty similar to the first chapter 11 problem that you're seeing here in the notes, or the second version. Chapter 13 was a really hard one to fit in. Its purpose was really to show us how the methods work for inference when we're dealing with a confidence interval or a hypothesis test. So I didn't really get a good opportunity to write in a good question. Instead, I have 2 questions in chapter 14. One question is going to be doing a confidence interval. I'll supply the Z star value. A second question is going to be doing a hypothesis test. I'll supply the p-value problem. And in both questions, you'll have to come up with what is the unknown population mean mu, the unknown parameter that we often call it. You'll have to give a conclusion for the confidence interval. You will say with whichever level of confidence, here's our conclusion. And same idea with the hypothesis test. On the hypothesis test, you'll also have to decide, based off the p-value I give you, would we reject or fail to reject? That would also be based off the significance level alpha. And maybe the trickier one question from chapter 15. It's going to be a question where we're analyzing the power of a test. So it's mostly a concept question. You'll have to say, what is a type 1 error? What is a type 2 error? And say in context. And you'll have to say, when I give you the power of the test, what does that really mean relative to the hypotheses and the overall context? But again, these problems have really similar, not really similar, but other versions of those same kind of problems as well. And best way to really practice these problems here is to be fully caught up on homework. So if you're a little bit behind, getting caught up on homework relative to those sections is far and away the very best thing you can do to prepare for this upcoming exam. The homework problems themselves are a great review. I'm not asking questions that are so wildly different from them. In fact, when I write those homework questions, I write them from the point of view of this would be a good exam question. Sometimes they're a little bit longer and I have to shorten them up on a real exam, but your homework questions are a great guide. And this is just extra material. This diagram or document right here, I haven't quite solved it. Well, I haven't even started, but I'm going to begin working on Friday. It should be posted sometime Friday afternoon at the latest. Well, that's my rundown on the exam. Other things I would say is definitely don't forget a scientific calculator of some kind, or a graphing calculator. I'm not too worried, but a scientific calculator at minimum will get you through any of the actual computations you'll need to compute. Well, any questions about the exam 2 content, folks? Any problems that we should visit, or any questions or comments? Okay, well, as far as the exam 2 studying goes, again, I'm going to be pretty busy on this weekend. When we're connecting from a week like this, going into an exam week, I'm busy too. So if you have questions over the weekend, if you're studying Friday, Saturday, or even Sunday, Monday as well, of course, don't hesitate to email. Even if you're working really late, say at 3 a.m., I'm sorry about the insomnia, but if you're working at 3 a.m. and a question just enters your mind, that's the best time to compose the email to ask about it. And I'll get back to you as soon as I check my email in the morning. I'll be working quite a bit on Friday, not as much on Saturday, but definitely in the morning on Saturday. And I'll probably be working quite a bit on Sunday as well. So those would be great opportunities to connect. And then again, Monday's completely wide open. I have office hours on Monday you could visit in, that kind of stuff. So now we're returning to chapter 17. But the work we're doing here, not too entirely different from the actual work we're doing on exam 2. This is a hypothesis test. You're analyzing a hypothesis test. Only big difference is, excuse me, some of the methods. For example, this is a paired dependent data. So we have slightly different methods there, slightly different methods for the test statistic. But a lot of the other stuff, like the interpretation, setting up the parameter, setting up hypotheses, entirely similar kind of stuff. So let's remind ourselves what we did in this problem. We're looking into the role of beta endorphin levels in the blood, excuse me, and its role on stress. So the interesting way that they measured stress is the researchers here took 19 patients about to undergo a surgery. And this is a real study. I need to look into this. I'm kind of curious what the full study would have looked like on here. I'm assuming the surgery was serious. Maybe everyone was doing an ACL ligament repair, something like that that's very comparable. These were their blood endorphin levels 12 hours before the surgery, and then 10 minutes, assuming right before they got anesthetized. This is their endorphin levels right after. Looks higher, but there's some interesting outliers, like patient 19. Really would like to meet that person. This person looks pretty stoic. Or I would be more similar to patient 8 myself. And some of these things kind of go backwards if you really look hard here. For example, patient 16 is more worried 12 hours before than 10 minutes before. Maybe this person just resigned themselves to their fate and they found some inner peace. Who knows? But that's what the study was about. We're trying to see the role in stress and blood endorphin levels. So we asked that practical question here. Does beta endorphin levels change with stress on average? Then we formed the parameter here. The data is paired, so we're taking the differences of the 12 hours levels minus the 10-minute levels. And so our null hypothesis is that nothing happens in the population. It's a statement of no change, a statement that the status quo is still the same. We're saying the differences are 0. Stress had no role in the blood beta endorphin levels. Here we're saying it does have a role. The researchers were asking for what effect? That means it's two-directional. Either it goes up or it goes down. And that's why we're doing a two-tailed test right here. We're going to check for both directions simultaneously. But then we saw some big problems. When we took this data and plotted it, here's the syntax. I had just a couple more comments about paired data. We're noticing that the data is, let's say right now, strongly left skewed. That's not enough to say it doesn't meet the requirements for the conditions of the one sample T procedures. What we now need to include in our discussion is the sample size, because we're discussing really robustness. Is the one sample T test robust against the deviation of normality that we see right here? It absolutely is if your sample size is large enough. Our sample size was at size 40, and we saw this histogram. That's actually okay. This is acceptable data right here. Robustness is actually powerful as these sample sizes get large, but our sample size is not large. Let's remind ourselves, RStudio is a fast way to check. It tells us in our data frame just 19 observations. So we must include that in our discussion. We'll say, since n equals 19, let's make it just a quick comment here. We must include this. So we take the sample size, we relate it on the guidance down below. This is pretty conservative. Our author is erroring on the side of higher samples for these kind of conclusions right here, because he's trying to work in lots of contexts at once. And well, we're not in this category for large samples. We have a sample size at least 15. Well, it's just 19. T procedures can be used except in the presence of outliers. Doesn't really look like anything too outlying for left skew. That's the shape I expect. Or strong skewness. That's what we're really looking at. And there could be an outlier by the 1.5 IQR rule of thumb. But the moment we see the strong skewness, that's the major problem right there. Let's say here, the one sample T procedures, let's say this is statistical method. So maybe it's better to say T methods to say that, but it's synonymous if you said procedures. The one sample T methods will not provide a reliable p-value. Our p-values are approximations in the first place, and the approximation is only good if we pass the robustness check. Now, doesn't look like they're going to be good at all. And that's kind of awful in a way, because look at our hypotheses. We're checking for a difference from 0 in any direction. here it is at 0. We have, looks like 5 observations above 0, but the majority are less than 0, 10 observations here, and skewing left is just in more support of being less than 0. This really is a picture of not equals right here. So there looks like there's a real effect going on, but the one sample t methods aren't going to give us a good view on the p-value. Well, let's say here overall, we remember we're discussing 2 conditions. Maybe I shouldn't have deleted that. Overall, the conditions are not met. And what about randomness? I don't know if we've even hit on that concept. Let's go back up to the context, see what we know about randomization. It says they took blood endorphin levels for 19 patients. That's all we know. We don't know how they grabbed those 19 patients. We hope they didn't just go to some like cardiac medical ward or something like that and grabbed who just happened to be there at that one moment in time. That might be tremendously biased, but we don't know. We have to actually get and look into the study. Sorry, I didn't provide much information there, but easy to Google. We'd have to look into the study, possibly buy the journal article and really read into it. We never do that in this class. We just go by what they give us in what's essentially an abstract. So we'll say here, no information on randomization. So we're not saying the authors did wrong. We're just saying they didn't tell us. That's our major conclusion there. We have no information. On randomization. And now we should give an overall conclusion of our assessment on conditions. I would say here, overall, the conditions are not met. This puts us in a weird position, right? Because we can run the test, we can give a conclusion, we can follow the guidance in providing a complete analysis and just mention after a conclusion, these are the ways you should probably not trust what we just did. But even if we did all that, you might feel like you're being just really disingenuous at that point, that you're doing an analysis you feel like you really shouldn't do, it won't work. Why do that analysis at all? So this is a weird opportunity in this class, but it's kind of fun in a way because it becomes really a choose your own adventure style of a problem at this point. So when conditions are not met, here's my guidance for you. When conditions are not met, 2 options. One option is do what I said first, run the method anyway. That seems awful, but let's keep on saying it. Run the method anyway, then mention the problems in your conclusion. And like I mentioned, that probably doesn't sit well with some people in this class. It just feels weird to do a method that you know is not effective. Why do it at all? It's for the purpose of just learning how it goes. That's my best answer. Here's another way to go, and you're perfectly welcome to take this second option. You have to pick one or the other. We're only providing one analysis to this data. But in option 2, run a non-parametric method. So what's the non-parametric method? What does that even mean? Well, our method, the T method, T procedures to do a one sample T test, it's talking about something parametric in the sense that there is a probability distribution with parameters like mu equals the population mean, sigma is another parameter for the population standard deviation. And we're talking about probability models like the normal distribution, T distribution. That's what makes it a parametric test for the one sample T methods that we set here. Now, if we want a different method that does not have parameters, that does not have probability models, we call it the non-parametric method. And the method that we would use here is Wilcox.test. Let me double check on that syntax. Wilcox.test. That's a O right there. And this problem, I want to show both methods just so that we can get a feel for how either one of them goes. And downside with the non-parametric method is that you are testing H naught, M as in the median, for the difference in the data is 0, versus HA, M, for the median of the data, not equal to 0. And M as the median of the data is kind of an okay thing to say. It's a decent interpretation, but it's not the entire truth either. That's one thing that's rough about a non-parametric method. The population median is a parameter too. It's describing the population. This isn't your normal median. M, we're calling it MD only because of the differences in the problem. So M here is the pseudo median. You can refer to it as the median in your conclusion or say pseudo median, but then you might have to give further explanation to your audience. And let me write down the definition of this thing. It's known as the so-called Hodges layman estimator. So lots of research to dig in to work into this non-parametric test, but this is a good opportunity to give a first discussion on it. So that's what we're going to do. We're going to run this data with the parametric method, one sample t-test, give a conclusion that doesn't look like it's too useful, omitting all the failures in it. Then we'll run the non-parametric method and see what kind of different conclusion we get there. We're going to say something about the median in our conclusion, but then we also should mention it's not exactly the median, it's a different thing, the Hodge-Lehman estimator. And so that should be mentioned in the conclusion as well. So condition checking is a wild adventure, and this is our first time we have a full stop. One sample t methods we don't expect to be effective at all. But just for the sake of showing how it goes, let's analyze the data anyways. Any questions first? Okay, let's keep on going. Carry out the necessary computations. So that's step 2. And let's hide example 7 down there somewhere. So for the necessary computations, we go back to our studio. Here's what the environment looked like after we did the plot for condition checking. We imported the data as stress. I think I remember having to do this a few times to get it in right. Then I added a couple comments here. We immediately took the difference, because the data is paired, of the 12-hour data minus the 10-minute data, gave a histogram of the differences, and it's kind of neat to say that the actual long title there works pretty well here. And now to analyze the data, we use t.test. Pass to t.test, DIFF, the differences. Next thing you want to give to t.test is information about your hypotheses, very important. Now, the default is the two-tailed test, but this is a really good habit so that when it's a left-tailed test or a right-tailed test, you're always knowing you're adjusting that type of test. Always write this in, alternative equals, I just hit enter here when it auto-completes, 2.cited. Hang on, let me double check on that. Alternative. And when we put in 2.cited, the cheat sheet here from our studio says it does need quotes around it. Kind of an interesting parameter we're passing. So go 2.cited, and that's our two-tailed test. And if this is at 0.05, you would also, if you gave a confidence interval analysis, want to write conf for confidence level equals 0.95. Again, that's the default, but if you had a different value for alpha and you were doing a confidence interval as a follow-up analysis, you'd want to track that change too. Really, best practice here is always give the alternative, match it up, even if it's the default, and always give the confidence level, matching up with alpha, even if 0.95 is the default. That way you always remember to change it when necessary. And that's the whole syntax. Hit Control A, Control Enter, and here's the entire output for t.test. The one sample t-test, like we mentioned, The test statistic is significant. That is about negative 2.5 standard deviations almost to the left. P-value is also significant. Alpha level was at 0.05, and we're below it. Maybe not by a huge amount, but we made it under our benchmark of evidence, 0.05. Also, there's a confidence interval for the differences. Because they are only negative values in that confidence interval, it gives us further information of why we rejected this one right here. It really is not equal. Everything is negative in that confidence interval, meaning the differences are negative. The differences are negative. That means that stress levels were higher at the 10-minute level than they were at the 12-hour level. So that's what all of this says. But now we feel kind of shaky on those conclusions, even though the graph supports it well, because t-dot test is just not robust against this level of skew. So this is the whole syntax for running it. Let's throw it in here. All we wanted was the hypothesis test, so I'll take a screenshot that goes like this. There we go. We've got the entire output for the one sample t-test. I recall lots of ways to do this part. The major thing I need is a t-test statistic and a p-value. So like we mentioned before in class, if you just put this on paper and this on paper, if you're writing it out just as a traditional assignment, that's totally fine. If you prefer to type things out, just type out your test statistic and your p-value at minimum, and you're just fine. And screenshotting, just make sure you have those things included. Let's just say it this way. Be sure to show the test statistic t and the p-value. So highly significant. Well, pretty decently significant. We can go now come up here, grab our information on what the parameter was and what the hypothesis test was, and give a pretty rapid conclusion. But then we shouldn't rest on that conclusion because we have to know there are some major problems with it. So let's say this is conclusion 1, actually. You don't have to do this twice. This is just for the sake of class. Conclusion 1 is going to be for one sample t-test. And conclusion 2 will be for the non-parametric test. So far, here's what we would say in this land. When we use the parametric test, we get a nice p-value here, definitely below alpha. So we'll say here, p-value equals 0.02497, less than 0.05, equals alpha, implies reject H naught. So there it is, it's gone. I'm putting it on list line above the conclusion because what we want is, by practical conclusion, something that you could tell anybody. Imagine those Jay Leno late night shows where they quiz people off the streets, seeing if they can embarrass them. You're just trying to give people information that's not going to embarrass them so they'll understand exactly what your conclusion is of the study. So we'll say here, we have found significant statistical evidence that the, well, mu d not equal to 0, we have to read that out. We can't give people technical syntax like this or notations, and Greek letters is not great either. So we'll say that the population mean differences or difference in beta endorphin levels and this had a unit, femtomoles per milliliter of blood for 12 hours minus 10 minutes before surgery levels. Almost there, that's a long readout, is not equal to 0. And if we looked into our confidence interval, that's providing the follow-up analysis, we could say the levels are negative. So we'll say is not equal to 0. Now, what was the practical question we asked? We asked, does beta endorphin levels change with stress levels on average? You know what? We did answer that, but you really have to think about this. Is that the world's most satisfying answer? Or if you gave this as a conclusion, would there be a follow-up question? Probably, right? The follow-up question is, if it's not equal to 0, is it positive or negative? What is your estimate of it? What is your confidence interval? All of that would be the follow-up analysis. And this is just really a reminder that when you do a hypothesis test, it almost never stands alone. There's usually a bunch of extra follow-up analysis, especially if you determined it was significant, that we actually have significant evidence. But on these kind of problems, it is okay to leave it like that. We addressed our exact alternative hypothesis. We addressed our original practical question. And it's an understanding that this is just a small part of what's a big problem. We're just looking into the hypothesis test. So let's do, in fact, we'll end it right there. It's okay if you said in your problem, the differences are negative because you looked at the sample mean differences or the confidence interval. But we're still not done with this conclusion because remember the challenges. This challenge, this conclusion, let's make this seem more dire. This conclusion is in major danger of being successfully challenged not so much because we didn't know information on randomization. That's just something we're going to look into. And because this was a published study, it most likely was random. It's just not in the abstract. The major danger here is because our sample data was far too skewed. Don't forget, it's not just about the skewness, it's the sample size as well. It was far too skewed with the given sample size. For our methods, let's just say method, to be reliable. So this is a pretty severe critique on our conclusion. We're saying that just about anybody that looks into this is going to see the problem right away and say that our work is invalid. And that's the reason why I feel like it's not the best conclusion at all. Like some people might not even want to get to that conclusion. We did it for the sake of just showing how it all goes, running through T-dot test, showing what the output looks like and analyzing it. Now let's do this in a slightly better way. The researchers probably did intend to do this kind of test, possibly back in the day when this study happened. And then when they saw the problems, they realized they had to make an adjustment on their analysis. That's never considered unethical. We don't know what the data looks like until we get it. And sometimes we do have to change our methods when we're forced to. So that's what we're going to do right now. So for conclusion 2, we go back to our studio and give a different analysis entirely. So here's our next run. Conditions were not met for T-dot test. Use a non-parametric method, and that's going to be Wilcox.test. test. So this is the next method we're going to run. Go Wilcox.test, test, and it's kind of nice that autocomplete is really fast on this computer. We pass to it, same thing, just the differences. And we should specify the alternative hypothesis just as before. I should go back to that. There we go. Keep in mind that I'm putting in two-sided, but the other information is you'd put in greater for the right tail test, you'd put in less for the left tail test. So it's just talking about the inequality in your alternative hypothesis specifically. But for ours, we'll go 2.tailed. And that's all I can say, because when it comes to this non-parametric method, you can get a confidence interval, but it takes a lot of extra work. It's more involved than digging into what's going on with this weird pseudo median estimator. Actually building the confidence interval requires us to install external packages into RStudio using other people's work and methods they built to make that happen. So there's a lot of trade-offs when you go to a non-parametric. The power of this test is way down as compared to the power of the one sample T methods. And if we did successfully get a confidence interval after a lot of work, a lot of additional packages installed into R, the confidence interval is going to be pretty wide on that as well. And it's not even estimating the mean. It's not even estimating the median. It's a highly specific estimator. But we can still run the analysis. Let me show you what it looks like. Uh-oh. Should be one of two dot. Oh, I put in tailed, cited. There's going to be another warning. There's possibly, there they are. So here's the Wilcoxon signed rank test. What they mean about that is they took all the differences and computed their absolute value. So now everything is positive, but then they looked into this value 0. Anything that was negative, once it got a positive value through the absolute value, goes into one sum. We're ranking all the negative quantities. Then we rank all the positive quantities and we just see which one's bigger. This is the test statistic. It tells us one side was bigger. If the null hypothesis was true, that the median really is 0, we should have expected some of the ranked sums, or excuse me, both ranked sums, and the negative side and the positive side to be about the same. This test statistic says there is in fact an imbalance. One side is larger. It doesn't say which side because it's checking for either direction. We just know it's significant. Curiously, p-value went down on this one as compared to the parametric method. There are warnings down below. It says, let's see here, cannot execute p-value with ties, cannot compute exact p-value with zeros. Well, ties would be because some of our differences were the same. The 0 came from this patient. They had a 0 value whatsoever, so it wasn't above or below 0. And this is RStudio just saying, well, we have given you an approximated p-value. This is inexact. So with less power on the method, strange things happening in the data causes an approximation to happen here, which is extra. But at least we have something. This is the real analysis of the pathological data we see here to the right. So that non-parametric method, let's use this syntax here to drop in our report. And for the output, we pretty much want just this whole thing right here. Notice it's not giving you a confidence interval. That's really hard to achieve for non-parametric methods, but not impossible if we must do it. So here's the output. And for the conclusion we can give, might be something generically like this. We have significant statistical evidence that, let me carry down one extra screenshot that we wrote in. We're running these hypotheses now. So this is a good reminder. When we go to give the conclusion, it's kind of a crash course on a non-parametric method. But again, this is mainly for the students who feel you wouldn't want to run the parametric method when it is just not valid. So it gives you an extra way to analyze these kind of problems when it comes up. Let's put that down below. So we'll say we have significant statistical evidence that the population, let's be honest, it's not the median. And if you said it was the median, it's pretty close actually, and people would really understand what you mean. But if I'm being honest about the complexity of what we did here, I would have to say the population pseudo median of the differences in beta endorphin levels and let's just remind us that this is 12 hours minus 10 minutes before surgery. So the pseudo median of the differences subtracted in that way. Let's take a look down here. And a hard time deciding what should be up top. It's below the 0.05, which is equal to alpha. So we will reject H naught and say it's not equal to 0. R naught equal to 0. That means there really is some effect going on in the population. And that seems a little bit more fair because even though we're criticizing one sample t-test heavily with our conclusion here, we can also look at the data and just kind of see most of the observations are to the left of the 0 value. It looks highly significant just by the graphics itself. And it's now finally supported by the right test, the Wilcox-Rake sum test. So we'll say, let's see, we have significant evidence that that population pseudo-median is not equal to 0. And what else would we say here? The p-value is approximate. We probably shouldn't say that. It's meant to be a practical interpretation. We should maybe mention one other thing. This conclusion may be challenged since we do not know how the data was collected. In other words, we still don't have any information on randomization, but one major problem at least has been corrected. It's also kind of reassuring that when we ran both tests, they both gave us the same conclusion. They were both significant. And so that gives us really good feeling that we are on the right track with this conclusion here, supported by a test that didn't run right. We have to admit that. A test that is ran correctly, and the p-value is even lower. And the graphics itself shows the significance as well. So we did it, folks. That's our first non-parametric method. We're going to counter more along the way as we go. This is optional. So if the one sample t methods don't work, you can still analyze it. Just mention the problems down below here, and you're always going to be totally fine. Even if it's dramatic, like what I said here, high chance of being successfully challenged. Well, any last questions at all, folks, with the stress data there? Kind of badly timed around midterm week, but at least it feels kind of immediate. For our last problem of the day, then, we're going to just do another hypothesis test. But this is a hypothesis test where we have no data. Well, we have statistics summarizing the sample data, but all the raw sample data is just not available to us at all. That means this problem here is similar to a real exam question. And differences on a real exam question are, let's see here, this would be exam 3. On exam 2, I can't ask you about the degrees of freedom or the standard error. Those don't exist in the chapter 14 methods. But I would ask you to calculate the z-test statistic, so we have to be ready for that. I'll supply the p-value on a real exam, so that's the major difference here. On a real exam, that's provided. Then you do the practical conclusion. So this one is a pretty interesting problem. We're going forward in chapter 17, but also does a decent amount of actually reviewing exam 2 content. This is the first problem of the entire course too, so it's kind of exciting to be able to actually analyze this data properly instead of just talking about it. The reminder here is we're dealing with a measure of health called the ankle brachial, let me try again, ankle brachial index. We're looking at the blood pressure in your arm, maybe measured here, to the blood pressure in your leg, presumably near the ankle. And the difference between those can be illuminating to what's going on with your health. It says a healthy ABI is 0.9 or greater. So that's our first bit of information. Now, this is just talking about one condition, but now we're going to the study and we're talking about the population for which this condition it might apply. And a study by these gentlemen, Leg Symptoms and Physical Functioning, in the Journal of the American Geriatric Society, gives us some kind of hint on the population maybe. Researchers obtained the ABI, ankle brachial index, of 187 women with peripheral arterial disease. So that's pretty important information for us. We can now write sample size N is 187. They tell us the conclusion. The results were a mean ABI of 0.64. Kind of rude that it didn't say sample mean, but we can read through the context. This mean is talking about the 187 women. That's not the population, that's just the sample. So that immediately implies this mean is X bar equals 0.64. It says next with a standard deviation of 0.15, same concept, that's the sample's standard deviation. So S equals 0.15. We have a 1% significance level, so we'll want to come back to that as well. So when it says 1% significance level, it's like a vocabulary check, really. We need to take that, recall that it's alpha set to 0.01, and that's where we're going to compare against a p-value once we get it. Question is, did the data provide significant statistical evidence to conclude that, on average? That word on average is actually very important because that's what we're measuring, population averages, or testing rather. Women with peripheral arterial disease have an unhealthy ABI. We'll take that, compare it with the above statement. Unhealthy ABI is less than 0.9. They're indicating left tail test here by that statement. I'm running out of space here. Maybe I can insert something here. So this is indicating left tailed test. So now we're ready to run through this whole problem. Actually, part A, we solved in class on the first day, but it's been a while, right? This is week, what is it? Week 9? I'm starting to forget at this point. So mu is going to be the true mean, or you could say population mean. I changed the wording here just a little bit just to signify you don't have to be stringent. You can add a little bit of color to how you say these things. U is going to be the true mean of, what's the numerical quantity? We go to the unit, which was ABI. We'll say true mean of ABI for all. When I say for all, now we're talking about the population. The all there being the big buzzword. What's the population? It's not the people with the 187 people with peripheral arterial disease. It's all women with peripheral arterial disease. So that's going to be our population of interest here. All women with peripheral arterial disease. Kind of nice they didn't give us another acronym for that, even though it's a pain to write out. Too many acronyms starts to get dizzying with these problems. So that gets us started. We have the unknown parameter. And on the real exam, that's going to be your first step too. Specify what mu is. We have to pull in the context. You have to say something about the unit. What is the mean of? Is it the mean of points? Is the mean of blood pressure, like in this case, or something else? And then you have to say, who's the population? Like we did here when we said all women with peripheral arterial disease. Next step is the null. alternative. And even though it's not required, this is just a good practice. Alpha equals 0.01 specifies a significance level. These commonly always go together. You want to read in what is your null alternative and benchmark for evidence all in one line. But if you left it off, I'm not too worried about that. The null hypothesis is talking about mu. So is the alternative hypothesis. Because the practical research question was about, do they on average have an unhealthy ABI? Healthy is greater than 0.9. That's why we go less than to check for unhealthy. And it's why we called it a left tail test in this problem. Less than 0.9. So this right here is mu naught, the value to be tested. On this one, you have two choices. Our author from our official textbook will always go directly equals to 0.9, which is jarring because if you're in the biometry lab, you are probably going greater than or equal to 9, and either response is totally fine. It's very similar to see them both ways. These textbooks just have to, or lab manuals just have to pick a way and stick with it. They're not always in agreement, but we really are conveying the same kind of information, because whether you said greater than or equal to 9, or whether you said equals 0.9, when we say we assume the null hypothesis is true, we actually mean that one. Even if you had a greater than or equal to there, the null hypothesis we assume true is directly at the equality itself, right at 0.9. We're trying to make our p-value as big as possible, in other words, by doing that right there. Now, this part is not on exam 2, but it is on exam 3. Degrees of freedom is referring to DF, is how we say it. So like a lot of problems, this is basically a vocabulary check to see if we know what the concept is for degrees of freedom. We take sample size minus 1, look up what we said the sample size was, and get 186 degrees of freedom. Pretty nice and large sample size. The conditions still might not be met, but that would be very unlikely, I would say, at this point. The data would have to be so tremendously bad that it's hard to imagine this happening with this kind of condition with real people. It's almost assuredly the one sample T methods would qualify for such a large sample size. Next thing we do is calculate the standard error. Standard error is the new thing we just picked up in chapter 17. It's the standard error of the sample mean, X bar really. Actually, let's use green for this. We usually compare green with something that's a standard deviation. And that's essentially what this is. It's the approximate standard deviation, or the sampling distribution of X bar, where we say, through the central limit theorem, X bar is distributed normally, mean mu, standard deviation sigma over root n. But new to chapter 17, as we admit, we don't know the value of that parameter sigma either. So we called this a new object standard error, where we make an estimate here and just go S over the square root of n. So that's the whole idea of the standard error. Go grab your S value, it's 0.15. Divide by square root sample size. This is a common mistake I make, put in 186. Make sure you put in the original sample size, 187. And this gives us standard error. It's really just a calculator problem. So at the moment, we're using RStudio as if it really is a calculator, like one you might bring to class. So 0.15 over square root 187 gives us this for the standard error. This is the approximate standard deviation of the statistic X bar. Let's see here, we're running to 4 decimal places. So I would get to 0.10110. I'm not sure if I said that right. Let me see if I write it in right. Let's double check that. 0.0110 upon rounding. Kind of an annoying round on that one. Does that look right to folks on the standard error? Okay, this takes us to the test statistic, T. The test statistic looks really similar to what you would do on exam 2, except that we call it T, then we go X bar minus mu naught, divide by the value we just found, standard error, X bar. And just like other parts of this problem, it's really just make the right substitutions, crank out your formula. So for X bar, we return to the 0.64 that we specified earlier. And notice how valuable this kind of is as a technique. I would encourage you to do this on exam as well, because what you don't want to do is every time you have to pull X bar, read this whole thing. There's just too many numbers. If I had to grab X bar from right there every time, I might miss and grab something else just on accident, like the 187. Who knows what I could grab? Maybe page number 222. This is directing your eyes to the actual value you're using repeatedly. Then go minus. That's a tough one right there. I wrote it in because that's how it's written into the formula. It's the value that goes here. Mu naught. It's the value to be tested. It's also the same value that's duplicated here. And we indicate it right up here. That's our mu naught value as well. But that's easy to miss because you usually don't use the symbol mu sub 0 often, except to specify a formula. And you might have done it right here, but maybe not. It's a good idea to actually write that in, because just like everything else, it forms a strong connection. The mu naught is just the 0.9. Sometimes that is a hard value to actually find in your problem. It's kind of strange. Then divide by this value, 0.0110. You might feel weird about dividing by that value because in your calculator, you can just use the store value to divide by. And I'm okay with either method. When you're doing this on paper in an exam situation, if you use the approximation down here, I would realize that I'm all right. If you use that value stored in the calculator by going, say, this, and then 0.64, divide by, or minus 0.9, divide by that. If you went that route, that'd be fine as well. You have a more precise value. That'd be something you'd want to definitely do if you're doing a homework problem. But even if this was a homework question, I'm not super picky about that. Let's see how close our approximation would get. 0.64 minus 0.9 divided by 0.01100. We are basically there. We're off by less than a tenth. So that's an acceptable value because when you look at either one of these, it's telling us that the sample data is essentially 23 standard deviations towards the left of the statement in the null hypothesis. This is huge, huge amounts of data, overwhelming amounts of data. So the difference between the two is not that big of a deal at this point. Let's go with negative 23.6364 using the rounded value. Let me double check. Okay, so that's lots of standard deviations. At this point, you'd have to question, do we need to calculate the p-value? It's probably pretty close to 0, but let's do it just for the sake of practice. It's a left tail test, as we can see right here. By the way, on the real exam 2, I supply the p-value. You just get down to interpreting the whole conclusion to the hypothesis test based on the supplied p-value. But here's what we'll calculate. The p-value is going to be probability, t distribution, and then we go and take your t-test statistic, negative 23.6364. We pass to it degrees of freedom, which was 186. And because it's a left tail test, our syntax is done. It automatically is going to get the area to the left, so we don't have to say anything about left dot tail. So just give the t-test statistic, degrees of freedom, and let's see what we get in RStudio. Probably scientific notation, so let's see the format of our answer. So go PT, negative 23.6364, 186, and look at the order of magnitude on that. That is 10 to the power negative 58. We're getting to the point where really close to not even be able to represent this number in this kind of environment. But let me just capture a couple digits And most importantly, the exponential notation. 3.15 times 10 to the power, I already forgot that magnitude, negative 58. If you've taken physics, you know that that is a pretty small value in terms of stuff like grams or centimeters. Power negative 58, that's a very, very small world you're looking into at that point. What was alpha? 0.01. That's assuredly less than alpha, right? We are well below any significance level alpha anybody would have provided that's reasonable. So we can say here, because we're about to do a practical inclusion, that the p-value is absolutely less than 0.01, which is equal to alpha. So we will reject H naught. You don't have to say that comment, but it's just a guiding set of thoughts before we jump into part G next. To really give that conclusion, we need a couple things. We need the statement of the parameter and the statement of the hypotheses. But we're pretty much there at this point. Let's read out what we're going to get. So highly, highly significant evidence, we'll say here, the study provides overwhelming evidence, or whatever colorful word you can come up with here, gargantuan amounts of evidence, something like that would be fine. It provides overwhelming evidence in support of the true mean ankle brachial index for all women with peripheral arterial disease. Okay, so we have overwhelming evidence in support of the true mean of all women with peripheral arterial disease being less than 0.9. And so in the unhealthy range. So what does this give the medical practitioners? They now know that if you have this condition, peripheral arterial disease, then they might as well check for a different condition, look into your ABI, because that might be quite off. Or if we don't know anything about that person, but we did measure their ABI, then peripheral arterial disease might be a condition to look into next, because it seems like if we look into these people with that condition, huge amount of evidence, their ABI is off. So that's a place to start looking. Doesn't give us any direct cause and effect conclusions, but it does give us now extra information about how these things might relate. Well, we did it, folks. That's the full rundown of an analysis for what a hypothesis test could look like as an actual exam question. Any questions or comments about it, folks? That complete rundown? Okay, well, congratulations. We did it. This is the end of chapter 17. Let's take a moment to appreciate how big these notes got. Down that left corner, it says it's 13 pages long. Not every section or chapter we're going to do is going to be that long, but kind of the idea was chapters 14 and 15 is just introducing inference, talking all about what is a hypothesis test, what is a confidence interval. Chapter 15 was all about how do you plan to actually conduct one of these tests. Now, chapter 17 is what does the actual method really look like? When we go into the follow-up chapters, we won't spend as much time because chapters 14, 15, 17, it's essentially the base of the course that allows us to now launch from here, look into other statistical methods where we just make small changes to all of our methods. Everything else is pretty much the same. And essentially that's what we're doing next. We're going over to chapter 18, handling two independent population means. We want to know if there's a difference between the two, or if we should think of the populations as being essentially the same. So here's that next chapter. in that chapter, same as this folder here, my thumb drive duplicates. I have one problem with raw data, it looks like. I also have a document. I'm getting into a habit of every new statistical method will have a document like this. And it's just a one-stop shop. If you don't want to open like the 13-page write-up of all the solutions, come here for some clean guidance on conditions about robustness, conditions on what is the whole method for the confidence interval, how do you implement it, in our syntax is given below. Same thing for the hypothesis test, some concerning formulas here. Looks like a typo I forgot to undo the red flagging on. And other syntax to implement either the two-tail, left tail, or right tail test. So that's going to be a common thing starting in chapter 17 and for every other new chapter as well. So next, here's how chapter 18 goes. It starts off a little bit slow because some of our formulas are so different in this section. I think it pays to pay a little bit of extra attention to say, how did some of those formulas change? We're going to talk about how the central limit theorem plays a big role in those formulas. And then let's take a quick tour of the notes. We need to generate a new standard error. Once we get that, we're in business for confidence intervals. Scrolling further, here are the new procedures. We take an estimate. We're trying to estimate mu1 minus mu2, two means. So that's the point estimate. We just take the difference in the sample means, multiply and subtract by t star, same t star we've been using, and wild modification on the standard error. That deserves explanation. That's why we'll talk about the central limit theorem on the first problem. Now, another big problem is degrees of freedom get complicated out of nowhere, but there's a reason for that. The two-sample t-test that we're running is not your ordinary two-sample t-test. If you've done this before in other contexts, you might have done other condition checking. And one of those conditions is a check for equal variance. Our analysis is going to sideline entirely the check for equal variance because our two-sample t-test allows for unequal variance in the very first place. That's why the degrees of freedom got really, really complicated out of nowhere. We're doing one p-value, not a p-value for a check on variance, and then another p-value for the test. We're doing just one p-value altogether. And that's a theme in statistical analysis. There are many p-values, then there's many opportunities for a type 1 error. Try to get it down to as few p-values as possible, and that's what this is achieving. It has an actual name that our author doesn't quite specify, but this is called, if you're curious to read more about it, RStudio also outputs this as a reminder. It's not the normal t-test we're using. This is the Welsh. I might have misspelled that name. I'll correct it once we get to it. This is the Welsh two-sample t-test. So, and once we run the Welsh two-sample t-test, it's also contained here in the confidence interval as well, except we just don't call it a test anymore. We just call it the Welsh two-sample methods. That includes both the test and the confidence interval. Now we're not worried about testing for equal variances whatsoever, and that's a really big benefit to us. Less p-values, less analysis. Even the check for equal variances itself has conclusions that have to be met. And even more concerning, we want to analyze data that doesn't have equal variances. Like these data are pretty interesting as well. There's no need to assume equal variances. We can still analyze the data as long as it has to pass robustness. If it doesn't pass robustness, we go to the non-parametric method, and those methods just get more wilder and wilder as we go. There is good news on robustness, however. Our methods with two means is more robust than one sample mean. That's incredible. And where the robustness shines is deviations from symmetry are much more stronger in robustness. So even if our data looks pretty skewed, we have more robustness than before on this. And let's say they're both skewed to the left, maybe both skewed to the right. If they have similar shapes, even better. We have a lot of extra leverage here when we're dealing with two samples and we're just trying to tell the difference. So what we do is we adapt everything we said about robustness in the last chapter, chapter 1, to two samples, By just adding together the sample sizes, n1 plus n2. So both samples get pooled together, and these are the checks that we're going to use here on combined sample sizes. So this is great information. It means the data can look even worse than our last problem where we had to use non-parametric, and we'll still be able to essentially get away with it. But where all of this starts is way up here. Central limit theorem still plays a major role in all of this. Other things to keep in mind is that we also need some results from probability. Probability is a pretty interesting subject. Here are the main results. The mean of two variables, x plus y or x minus y, is just the mean of the x variable, add or subtract the mean of the y variable. There's two values here just to compact two formulas. If it's plus, we use plus here. If it's minus, use minus here. Variance, we haven't talked about a lot, right? But variance is just the square of standard deviation. So if sigma is the standard deviation, it's a parameter, so of the population, then sigma squared is the variance. We introduced it, but again, we talk more about the standard deviation than the variance. Probability theory works a little bit more on variance than standard deviation, so it's kind of a context-sensitive thing. Notice what happens to variance, though. It doesn't matter if you're adding or subtracting. The variance is the uncertainty, how one individual is different from the next, and variation always adds, even if you're subtracting the variables. The uncertainty just mounts the more variables you put in. So even if you're minusing, variation only goes up. It can never go down. This is wild thoughts as well. Again, it might make a lot of sense if you've taken probability theory. If you haven't, this might seem kind of vague. And if that's you right now, let me know. I can give a little bit more information, post a write-up on the Moodle webpage on what's going on with this thought right here. So finally, if the variance is that, and to go from variance to standard deviation is just taking a square root, we take that whole equation here and say the standard deviation of x plus or minus y is just the square root of the prior step. This is kind of the hint on why our standard error looks like this. It's just a big consequence of dealing with multiple variables in probability theory. Now, here's what we're going to do on this problem. It says gather two independent. This is the essence of this section. We have two independent simple random samples. Sample sizes go n1 and n2 from two populations distributed normally. We can weaken that through robustness, but we're going to just start by saying they are normally distributed. We want the sampling distribution of the following random variables. Well, x1 came from here, and so now we can say this is a central limit theorem statement. x1 bar is distributed normally. True mean mu1 will take on the standard deviation sigma 1, and then we'll divide by the square root of sample size n1. Let me make that 1 apparent. So again, this is just the good old central limit theorem applied right here. And this feels redundant, but we have to do it twice. Here's the second time. X bar 2 is also distributed normally. Here is its mean, mu2. Its sigma value, sigma 2. So we'll say it's mu2. The only danger here is messing up the subscripts. Sigma 2, let me know if I do that at any point. Divide by the square root of sample size n2. So that's just the central limit theorem in action. And now down here, what we really want is the sampling distribution of the difference in the sample means. This is the sample distribution of x bar 1, x bar 2. But to get our methods kickstarted, we need it again for down here. Let's start by saying the mean of x bar 1 minus x bar 2 is, using this information, think of capital X as referring to this variable, x bar 1, capital Y is x bar 2. We just take their appropriate means and either add them or subtract them. We are subtracting because we're trying to find the difference between population means. So we'll go here and say it is mu1 coming from over here minus mu2. So we've got the mean down. That's the thing that goes in the first law. So we're halfway done specifying the distribution. It will be distributed normally. Any linear combination of normally distributed variables is again normally distributed. So that's a nice fact. Again, this is just a bunch of stuff from probability theory, making it kind of rough as well. But at least we get to see the role in the central limit theorem. We need the standard deviation, but we actually have to go to the variance first. So let's start by saying the variance of x bar 1 minus x bar 2 is, we sum the variances, go to the first value here. That's the standard deviation, not the variance. So I need to square it to actually get the variance. So go, let me try again. So go here, take that standard deviation, follow this logic, square it to get its actual variance. It'll be sigma 1 squared over n1. And then variation only goes up. Uncertainty always goes up the more variables you add. So we go plus, despite the fact we're subtracting our sample means, then add the square of this one, sigma 2 squared over n2. Then finally, we can get the standard deviation by just taking this result, square root it. That's what we're square rooting down below here. So we'll say the standard deviation of x bar 1 minus x bar 2 is square root of sigma 1 squared over n1 plus sigma 2 squared over n2. At this point, we're about there. We can say x bar 1 minus x bar 2 is distributed as, that's our tilde there, also the normal distribution. That's a big probability theory theorem. But the other thing that we got was we could put in the mean now. The sampling distribution of x bar 1 minus x bar 2 is centered at the thing we want to estimate in the first place, mu1 minus mu2, the real difference in the population means. And the standard deviation is this whole thing, square root sigma 1 squared over n1 plus sigma 2 squared over n2. This gets us started, and now we can call this result here the central limit theorem. For a difference in sample means. That deserves an exclamation mark, because if you can state the central limit theorem for the statistic you're analyzing, and if the center of that distribution is the actual parameters you're analyzing as well, you are ready for statistical inference. This is all you need to crack this open. We can do confidence intervals, we can do hypothesis tests. We just have to estimate that. We don't know what it is. We don't know what mu1 is, mu2, so we don't know what their difference is. We certainly don't know what sigma 1 or sigma 2 is, so all of this is unknown, but we can still overcome that. The t distribution is going to allow us to say, if we use the estimate, S1 is approximately equal to sigma 1, S2 approximately equal to sigma 2. That's two big estimates, but the t distribution captures the error in making those estimates. So now we can say, for the standard error of the difference in sample means, we'll indicate this by saying SE, x bar 1 minus x bar 2, or just reading it out, is equal to the square root of. We make these estimates right here. We're using the sample data, and we just plug it in right up in this location. It's S1 squared over N1 plus S2 squared over N2. Once we gather the sample data, this is computable, and it's just approximation for the standard deviation of this sampling distribution. So now we are ready to go on our methods. Except I have to admit to you, there is one interesting thing happening here. That is a wild derivation. We're not going to derive what's going on there. It's just a ultimate consequence of upping the complexity by dealing with two different means simultaneously. So it's going to widen our confidence interval even further. We've made two big estimates. And that structure there was for the right degrees of freedom. Pretty strange for a formula though. But any questions at all, folks, on the development so far, getting to our newest standard error? Okay, well, this will be our stopping point for today's work. And just to throw out there, if you are studying for exam 2 over the weekend, don't hesitate to reach out. I'm going to be available. I'll be working, I think I said already, a lot on Friday, a good amount on Saturday morning, and a lot on Sunday. So reach out anytime you are studying, encountering a question, getting caught up on homework, anything like that. I'll be happy to help out. But have a great weekend, folks. Try not to work too hard if you can help it. And I'll see you all on Tuesday. Well, I should clarify, if you're in the online section, we won't have a Tuesday's class. We'll just have an exam on Tuesday, so there won't be any Zoom session. Take care, folks. I'll see everyone on Zoom in a week away from today.